Hey there, it's Jason Gorman from Codemanship with the third video in my series on unit testing for COBOL programmers. In the first video, we looked at the basic idea of unit testing and the anatomy of a test suite in COBOL, where you have test procedures or test paragraphs, test fixtures, which are modules or programs that contain a number of related test procedures. And then that would be organized into test suites that would execute all of the different procedures and all the different fixtures. Here's an example of one, which is for testing a square root calculator. And we've got 6 tests here, 6 test procedures: square root of 1, square root of 0, square root of 4, etc., etc. And if we take a look at these tests, what we can kind of see is that they're all very similar. The only thing that's really different is the name of the test, the input number, and the expected result. Those are the only differences, really. So we've got quite a lot of duplicate code in this test. We've got duplication of test procedures. These are all of these test procedures are different examples of what is effectively the same test, the square root of a number. Now, if we wanted to refactor this to remove this duplication, one simple way that we could do that would be essentially to parameterize one of these tests, so that rather than setting the numbers like we're doing here inside each test, we're actually passing the numbers in. And a simple way to do that in COBOL would be to use a table of numbers to represent our test data, to represent our test cases. And then we'd have a single test, and we'd loop over that table and perform the same test with different input and expected output values. So let's take a look at a refactored version of this test fixture that uses a parameterized test. So in our parameterized version of this, what we've done is we've set up a table with our input values, the number here, and the expected output values, the route that we're expecting to get. And we've got 6 examples of this, which we're then redefining into a table with 6 entries. And all we're doing inside our test code now is we're performing the same parameterized test using these values, the number and the route for each of those test cases, from 1 to 6, basically. So we're looping over the table, performing the same test 6 times with different values, different data values for our tests. And we're also calculating the name of the test dynamically here, you can see. So we're actually calculating a test name that's displayed when one of these tests fails, so that we know which test case, which input value we were talking about. And I can just demonstrate what would happen if one of our tests fail there. So I'm just going to change one of these test data values to be deliberately wrong, and let's see what happens. Let's just rebuild that. Thank you very much. And then we'll run our test suite here. And there we go. We get a test failing, square root of 0.25 test, expected 0.7 but was 0.5. So that gives us a very clear idea of which one of those test cases caused the failure, so we don't get lost. And that's the basic idea of a parameterized test. Essentially, we set up tables of test data values with 1 row for each test case. So equivalent to the original test. Each of these rows in here represents, each pair of values, if you like, represents one of the original tests in the version I showed you before. And all we're doing is we're looping over that and executing the same test with different data values. So this is sometimes referred to for that reason as data-driven testing. It's a very useful way of removing duplicate tests from our code. So if we've only got 2 or 3, it's probably not worth bothering. But if you've got half a dozen or a dozen tests that are just different examples of the same test, just the same rule, if you like, being tested, but with different data values, then a simple way of removing that duplication and shrinking down the amount of test code that we need to support is to use a parameterized or data-driven test like this. So fairly straightforward. And once we've opened that door, let me just change that back so that it doesn't fail again. Once we've opened that door, it is actually quite straightforward to add new tests. So if we wanted to add a test for square root of 25, for example, it's now much easier to do that. We don't have to write another test procedure. We can just add another row, if you like, to our table. That's wrong. So we don't need to write any new test methods. We can just add them dynamically like that. And if I recompile that, we should end up with one more passing test. Thank you very much. Let's go back to our suite and run that. Okay, there's only 9 tests. That is interesting. It hasn't added another test. Let's just double check that. Recompile. So there should be an extra test now. There should be 7. I know what I've done there. Now, this is something I find quite annoying about COBOL tables, but you can probably think of a smarter way of doing that using the length or the size of the table. So you don't have to remember to do that. Let's recompile. Okay, now when we run our test suite, we should get an extra test. There we go, there's 10. So it's relatively straightforward now to add more tests. So we can buy ourselves greater test coverage relatively cheaply with relatively little extra code. Now looking at this is all fine, but let's just say for the sake of argument that this square root calculator is going to be used in some kind of critical application. Or in a critical part of the code for our application, what we call load-bearing code. Would those 7 test cases be giving me a warm, fuzzy feeling that our square root calculator definitely always works? I'm not sure. I'm not getting that warm, fuzzy feeling. So I think I probably want to write more tests. And as easy as it is to add new test cases just by adding new rows to our table, if I wanted to do, say, 100 test cases or even 1,000 test cases, that would get very laborious. So the final thing we're going to look at today is a technique called property-based testing, sometimes referred to as generative testing. And what we're actually going to do is, rather than hard coding our table of test data inputs, we're actually going to write code to generate the test data programmatically, a little algorithm that's going to generate our input values, so that we can do as many test cases as we like with very little test code. Okay, so what I've done here is I've adapted the original data-driven test, the parameterized tests, so that instead of reading our test input values, our test data from a table, what I'm actually doing here is generating that data dynamically in a loop here. So we're looping from 1 to 100 as our input values, and we're testing for each of those input values. But in order to do that, you may notice I've had to make some subtle changes to our test here. Rather than testing for an expected square root, because that would require me to sit down and calculate all the square roots from numbers from 1 to 100, which I don't particularly want to do. What I've done instead is I've made the assertion here about a property of a square root. In this case, what we're saying is, if we were to multiply the square root by itself, it should equal the original number. So we're comparing root times root with the original input number in our assertion to see if that indeed, if each of our calculated square roots has that property. This is called a property-based test. It's when the test makes an assertion about some general property that any correct result should have, so that we can then very easily generate the input data and then drive our code, drive our tests just using the inputs without having to know in advance what the expected outputs are. So it makes it much easier for us. So having adapted this into a property-based test, let's just compile this. And I probably need to recompile this as well because I made a change to it. We'll talk about that in a second. And okay, so let's go back to our square root test here. And what I'm going to do is I'm going to run our tests now. And whereas originally we had 9 tests in our suite, 6 of which were for our square root. This time we're going to get 103 tests. 100 tests will be for our square root. So let's run our test suite, see what happens. There we go. So, oh, interesting. Okay, let's look. A lot of these tests are failing. Square root of 77, for example, 78, 85. So about a fifth of them, 20%. 22 of them are failing. But if you look, they're very close. So what we can see going on here is some kind of floating point effect. Now, when I discussed this with our customer, let's imagine, the customer told me that these calculations, this needs to be accurate to 2 decimal places. So I've specified in our assertion now an extra piece of information, which is the margin for error, which in the case of these tests is 0.01. So as long as it's within that margin, we would say that it's okay. But what we're seeing here is that a lot of our results are not within that margin for error. They're not accurate enough. So what we could do to fix this is we can add a little bit of extra data, add another floating point 0 to the numbers we're using to do the calculation, and let's do that for our square root algorithm as well. So we've got a little bit of extra give, a little bit extra wiggle room in our floating point calculations here that hopefully will mean that we get within our margin for error, within 0.01 for our final result. So let's recompile that. And we'll recompile that. And we're going to run our test suite again. So what we're doing here is we're creating extra wiggle room in our floating point calculations, which hopefully will bring our results within our margin for error. So let's rerun our suite of tests. Okay, now a lot more of them are passing, but there's still one test failing, and that is a very curious one. The square root of 2, for some reason that's not working. It's way off. Now, I don't know why that's working. I would need to go in and debug this to figure out what's gone wrong with my algorithm there, and I'm not going to do that in this video, don't worry. But I just wanted to demonstrate here, by my original suite of, my original test fixture had 6 tests for square root, which was fine, it gave me some confidence. But what we've discovered here by doing a property-based test, by doing a more exhaustive test, is that we've discovered one test case that it doesn't seem to work for. And we now need to figure out why is that one not working. And we wouldn't have spotted that if we hadn't have gone further. So for the parts of your code that are more critical, that really, really need to be very reliable, you might decide to use this technique, property-based testing or generative testing, to generate your test data inputs so that you can do much more exhaustive testing and find those cases that your original test cases might have missed. So it's a very powerful technique, very, very useful. And there's one final thing I want to demonstrate here. Let's say that all 100 of our tests are passing for the square root algorithm, and that gives us a nice, warm, fuzzy feeling. But then maybe we find out that the code is even more critical than that. So the next question might be, how much extra code would I need to write? We've got 100 tests. What if I want to add another 900 to make it 1,000 tests? Well, now that we've opened this door with our property-based test, in actual fact, it's very easy to do that. All I have to do is add another 0 there, as simple as that. So now we're going to go from 1 to 1,000. So let's recompile that. Okay, rerun. And something's gone a little wrong there. I know exactly what's happened here. Good old COBOL. So in my copybook here for the test stats, I've only allowed 3 digits for the count of test numbers. So we need to add another digit there. The joys of COBOL. My own little Y2K bug appearing there. So now that we've got thousands of tests, or more than 1,000 tests, we need some extra space. That means I need to recompile everything that was using that copybook. Off we go. So let's recompile all our tests. and square root tests. Be jolly nice if the feature in Open COBOL that compiles all of them from the program you select, all the all the libraries, it doesn't actually work, unfortunately. But it'd be nice if it did. Okay, so that's everything recompiled. Let's rerun it, and we should now have, there we go, 1003 tests. Again, the same test is failing as before. So it's very, very easy, once you've opened this door to generative testing, to buy yourself quite mind-boggling amounts of test coverage with surprisingly little test code. And we don't have to just do ranges of numbers. We could probably generate random inputs. If we have logic that has combinations of inputs, we can generate all the different combinations programmatically. So there's quite a lot we can do if we put our mind to it to generate the test data on the fly, as it were, feeding that data into a property-based test so that we can get really exhaustive coverage. We can explore much more of the state space of our application while it's running and get ourselves very high levels of test assurance for that code that has to have very high integrity. So there you go, two very useful techniques. If you see a bunch of tests that are all essentially different examples of the same test, like our square root tests were, you can consolidate them into a single parameterized test and use a data table to drive that test. For code that's very critical, what we call the load-bearing code in our application, and most applications have some load-bearing code, we can go one further than that, and we can change our parameterized test into a property-based test, a test that asserts some general property of the correct result. For example, I reversed the computation of the square root to see if it matched the input. And then you can buy yourself quite mind-boggling amounts of test coverage, very high levels of assurance, surprisingly cheaply with very little extra test code. So two very useful techniques for the code that requires it, for the code that needs it. You wouldn't do this for all your code, of course, but there are occasions when these techniques come in useful. So there you go. That's 3 videos about unit testing in COBOL. You now know how to write unit tests and build test fixtures and test suites in COBOL using very simple design techniques. You know how to exclude external dependencies from your tests by injecting in the names of the modules that have those external references, so that you can essentially test your core logic without talking to databases or without hitting web services or anything like that. So we learn how to use test doubles, stubs and mocks, to make our unit tests genuinely fast and to exclude those nasty, complicated external dependencies. And then finally, we learned how to consolidate our similar tests into parameterized tests, and how we can adapt those parameterized tests when required to turn them into property-based or generative tests, so we can get a lot more test assurance. We can cover a lot more ground with surprisingly little test code. All those techniques put together with a few more smarts would allow you to test the bulk of the logic in your code. So I hope these have been of use. In the videos that are coming up, in the next video, we're going to talk a little bit about legacy code and a technique, a little sort of algorithm for making changes to legacy code safely. And then we're going to get onto this whole topic of test-driven development in COBOL. So I hope that's been of some use. I will speak to you in the next video.